Good afternoon, Ms. Michelle Lee, JP, Permanent Secretary for Education. Professor Wang Yang, Vice President for Institutional Advancement at the Hong Kong University of Science and Technology, guests, teachers, and students. I'm Ms. Wang Chui Ping from the Mathematics Education Section of the Education Bureau. Welcome to the 7th lecture in the Distinguished Lecture Series on applications of mathematics in STEAM world. Today, we are honored to have Professor Wang Yang as our speaker. The topic of today's lecture is Generative AI and Mathematics. First, we would like to invite Ms. Michelle Lee, JP, Permanent Secretary for Education, to deliver the welcoming remarks. Ms. Lee, please.
Professor Wang, principals, teachers, students, and colleagues, it is indeed my great pleasure to welcome you all at today's distinguished lecture series on application of mathematics in STEAM world. First of all, I would like to thank Professor Wang Yang for joining us today to share with us his insights into advanced development in artificial intelligence, or AI in short, and the mathematical underpinnings. Professor Wang, as you may be aware, is a well-renowned mathematician and expert in data analytics and machine learning. He currently serves as the Vice President for Institutional Advancement and Chair Professor of the Department of Industrial Engineering and Decision Analytics at the Department of Mathematics of the Hong Kong University of Science and Technology. I'm sure we will all benefit and be inspired by Professor Wang's sharing. To align with our national strategy of rejuvenating the country through science and technology, and also strengthening the country through talent, or 科教興國，人才強國戰略, the Education Bureau is committed to stepping up the promotion of STEAM education in primary and secondary schools. We have implemented various measures, including, we have reformed or revamped the curriculum, both in the primary and also the junior secondary, schools. For example, we have already introduced AI in junior secondary, and we are going to do so, in the upper primary as well. And we will also enrich our curriculum and also a lot of the teaching and learning materials in science and technology. I think all of you are secondary school students, right? I really envy those, primary school students who are going to benefit from our, curriculum reform, which is going to be introduced in 2025-26, because we're going to introduce an independent subject on science. We hope to inspire the curiosity of learning, in science. And at the same time, we have been promoting the wider use of innovation technology, or INT, in learning and teaching. Mathematics education, in particular, plays an important role in STEAM education. Whether you want to be a banker, an economist, or a public administrator, or a professor, or you would like to work in the Hong Kong Observatory, or you work in the transport industry, whether it's local, road, marine, aerial, aerospace, outer space transport, or whether you would like to work with material science, or in the medical field, like the MRI, etc. You can't do away with mathematics. And today we're really privileged to have Professor Wang with us, because he's going to talk about mathematics as related to AI. We learn ABCDs in kindergartens, but the new ABCDs in this modern era mean A, AI, B, blockchain or big data, C, cloud computing, and also, of course, D, like data analytics. And today, Professor Wang is going to talk about AI, and also he's an expert in data analytics. So you're really privileged to be here today. And to help teachers and students deepen their understanding of how mathematics is closely related to daily life situations and the importance of mathematics across different disciplines, the EDB has organized a series of lectures like today. Today is the 7th, right? The 7th in the series on application of mathematics in the STEAM world. And under this series, we are really privileged to have a lot of distinguished scholars and experts from different fields. You know, if you have to look at it or to read the textbooks, it's very difficult to understand. But if you can hear, from the experts, and you can also ask them questions, I'm sure Professor Wang would welcome some questions from the floor. So you will learn more about how mathematics is actually related to the world, in engineering, material science, as I mentioned. And I'm sure, the experts' insights would help our students recognize the relevance of mathematical applications to the future studies and careers. For those of you who are still thinking about, future career, I really recommend you to take mathematics, M1, M2, at least M1 or M2, okay, if not both. You can't take both, I suppose. But really, it is very, very important, and it will broaden your choices of disciplines in your university years. It's never too late, okay, if you have not yet chosen. And in the contemporary world that is increasingly shaped by technology, where AI and intelligent automation are transforming industries, mathematics has become an indispensable force driving innovation and progress. It's not just an abstract concept, but it's actually some kind of very useful and dynamic tool that connects us to the real world. Professor Wang, our distinguished speaker today, is going to let us know how mathematics amazingly elevates the development of AI. And being a mathematician himself, Professor Wang's groundbreaking work in data analytics and machine learning exemplifies how mathematics underpins technological innovation. And his research illuminates the profound impact of mathematical principles in reshaping our digital landscapes and contributes a lot to the development of cutting-edge technologies, particularly in AI and big data analytics. And I hope that, by listening to Professor Wang's lecture, you will also reflect on his sharing experience. I encourage you to view mathematics not as some kind of just manipulation of strings of some code symbols. It's not something cold. It's something which is very more tangible. If you think about what you use in daily lives, you can still find mathematics in and out of what you use today. And you will find and also acquire the essential knowledge and skills to analyze data, predict trends, like, if it's going to be colder or cooler today, we need the Hong Kong Observatory's prediction using a lot of those data analysis driven by technology and also a lot of mathematical principles underpinning. So, dear students, let today's dialogue spark your curiosity to explore the connections between mathematics and AI, and also dive deep in mathematics application in technology, science, finance, and beyond, and embrace the beauty of mathematics as your pathway to understanding and shaping the world around you. And once again, I would like to express my heartfelt gratitude to Professor Wang for an enlightening talk ahead. I also encourage teachers to actively participate in our upcoming lecture series and continue to explore how mathematics education can be integrated with innovation and technology. And together, we can provide students with more inspiring learning experiences, which will guide you to pursue your dreams. As Christmas is approaching, may I also take this opportunity to wish you a Merry Christmas and also a happy, prosperous, and fruitful 2025. And wish every one of you good health and happiness. Thank you very much.
Thank you, Ms. Lee. Would Ms. Lee please remain on the stage to present a souvenir to Professor Wang? Please remain on stage for a good photo. Thank you, Ms. Lee and Professor Wang. Please take your seat. We will now take a group photo that includes all our guests and participants. Oh, okay, thank you. Now, let's begin the lecture. Please give a warm round of applause to welcome Professor Wang. Professor Wang, please.
Thank you, Michelle and colleagues from EDB, teachers, students. It's a great honor to be here. Actually, this is not an easy talk because we're talking about mathematics, and I know you are all either teachers or high schools, so you probably don't have some of the technical, really technical background, and I'll try to do the best I can to convey how mathematics is used, but also, without dive into all the details. But I hope, after I did spend a lot of time prepare for this talk, and I hope by the end of the day, each one of you will get a sense how important it is to learn science and mathematics. Okay, and so let me. Do I turn this on? How do I do this? Okay. Yeah, please take a look at this. Okay, so I'm not an artist. Okay, I don't know how many of you here are artists. I cannot draw, but I did this nevertheless. I created in the beginning of Year of the Dragon, of course. I created these two greeting cards. Actually, not this one. I mean, this one. Okay. I used a AI tool called DALL-E, created by OpenAI. There are many others. There's something called a Stable Diffusion. There's something called Midjourney. Many of you have already been using. If not, I highly recommend. And I actually would like to give a public lecture, completely public lecture to students about how to use these AI tools. You don't need to know any mathematics or any physics or computer science to be able to use it. However, these will help you learn. Okay, so you can see it draws a dragon, sort of coming out of the ocean, and a rabbit, which was, the year before was swimming away. And my name is, this is my name, Wang Yang, right? So I asked ChatGPT to come up with a greeting, and this was created by ChatGPT. Okay, so you see, I'm a completely ignorant in terms of arts, but nevertheless, everybody said, "Oh, this is a great greeting card you have made." Okay, of course, later on, I was pointing out that this is really a Western dragon, which symbolize evil. And in the Chinese tradition, dragons should be this, which is, it doesn't have wings, which symbolize benign and benevolence and generosity. Okay. So anyway, that's a little detail you can play around with. Okay. So AI, everybody is talking about AI, but I bet you that 6 years ago or 5 years ago, not even the teachers, or maybe I would say 6 years ago, not even the teacher were talking about AI. Okay, why is that? Actually, AI has gone through a bunch of up and downs. Okay, and you can see from 1956, in fact, in Dartmouth, the conference was the first time it coined the term AI. Artificial intelligence. And since then, it got, you can see this is what we call the first winter of AI, okay? Then, this is an interesting period. This is the period where I was in the US. I grew up in China, and I went to, after graduation, I went to Harvard to do my PhD study in 1983. So one of the very first courses I learned, even though I was a math student, I decided to take some computer science because just felt this might be something I would need. So I took a course on expert system. Okay? Now, what is expert system? At the time, it was very, very hot. So this was the sort of the second summer of AI. Okay? And what expert system does was to say, let me give you a simple example. Some of you go to hospital. You take an X-ray image, and you want to know from the X-ray image whether someone has, let's say, cancer, for example, okay, or other kind of lung disease, and you would ask medical experts, say, do you think this person has cancer? So the expert would look at it, say, oh yeah, I think this one doesn't have, or he has it. So then you ask, why do you think that? So the expert would tell you, if I look at these black spots, I look at these white spots, I look at the, these different patterns, and say, if I see this pattern, I see you have, you're likely to have cancer. If you don't have this pattern, you're completely normal. And then you begin to ask 20, 100 experts to ask each of them how they detect cancer from X-ray. Then you input all these together into a system. You try to mimic the experts. This is called the expert system. Sounds great. Guess what happened? After a few years, they found the expert system to be completely useless. Okay, it could not even beat an entrant medical student in reading those X-rays. Okay, or some other. Of course, expert system don't mean just medical. It could mean something else. Okay, but in any case, then it got into a deep winter. This is one of the longest winters. Nobody even talked about AI for a long period. When you graduate, you say, I'm studying AI, you can't find a job. Okay? That was what happened. Then until at the time, so in 1997, IBM developed this software, this chess player called the Deep Blue. It actually beat the world champion Garry Kasparov at the time. So then it revived a little bit, but it still didn't quite go that far. Then, just sort of stayed a little bit lukewarm, and until really the machine learning era. And machine learning is what I plan to spend some time to talk about today. And of course, the real deep interest, this is sort of really the pinnacle of the summer of AI, the deep learning era, and especially since ChatGPT came up. Okay, so the ChatGPT era, in my view, we're entering the fifth industrial revolution because of the large language model, which we call ChatGPT is a large language model. Okay, so these are some of the, I just made a quick summary. So you can see the first wave, the second wave, and characterized by expert system, and now is really the deep learning, the GAN, generative AI, but in particular, what I consider to be a pivotal moment in the AI history, that is large language models. Okay? All right, so let me continue to tell you a story. This was a very famous article in the New Yorker. New Yorker is a very high quality magazine in the U.S. And what happened was, so this person is very famous. The author is she writes about the medicine, and she has a book on cancer, which is supposed to be the Bible of cancer for the layman. Okay. And so in the story, it mentioned in this article, it's a very long article. It mentioned a story that one day, this was before the AI era. A patient, a woman in New York City, had a severe headache, just suddenly a very, very big headache. And she was rushed to hospital, to Columbia Hospital. And the expert looked at her, took all kinds of, images, okay, diagnosis, and nobody could find anything. So in the end, the expert gathered together, talk about, looking at all the signals they collected, the 脑电图, EEG, and the various heart scans and everything. So only one graduate student, a Chinese graduate student, look at her, this patient, say, oh, something is wrong about this person. But then the professor presses the person and say, where did it go? Where do you think it went wrong? And she said, I really don't know. I can't tell, but it's my hunch. And so in the end, they decide nothing is wrong with this lady. Just send her home. 2 days later, she died from a massive stroke. Okay, so basically, at the time, there was no good tools to identify, to diagnose these kind of problems. And so this highlights the weakness or how useless those expert system was. So why we have made such a jump, and this is where mathematics come in, okay? So the second wave started when they look at these X-ray. Let's continue with the X-ray story. They look at X-ray about lung cancer or tuberculosis or whatever. And this time, they no longer trusted the experts. Okay? They say, we don't want to hear anything from the expert. We want mathematics. Just tell us this image, you have taken this person, you actually did additional tests, whether this person has cancer. Just tell me, just give me a bunch of images. Tell me which one has cancer, which one don't have cancer. Just tell me the data. I don't need the expert tell me how he thinks this person has cancer, this person. And just use that information because the rest is done by computer, what we call machine learning. So the machine will take your input classification and find the pattern that, typically explained by the expert, but not very well, and actually come up with a diagnostic tool to say, oh, you give a new one, because it learned all these images, and say, oh, this one has cancer, this one is completely normal. So this is actually the beginning of the machine learning era. Okay? But what is the mathematics behind it? Okay, so I hope I'm just going to give you a little bit of background here. Okay, so we talk about black box. We don't like black box, right? Everything has a reason. Okay, why the mainland tourists don't come anymore. We try to rationalize. We think, oh, the economy is over there is really bad because they don't, they lower their consumption. We think, why Americans elected Donald Trump? Because, well, blah, blah, blah. You say all these things. Okay? You think you know. But the expert system story told us we actually don't know. There are so many factors that we try to rationalize them in 2 or 3 simple factors. It just doesn't work. Okay? So the whole idea of machine learning is to say, well, let's not pretend we know everything. Let the data tell us what we should know or how things work. Okay? And as a result, we come up with something most people believe to be a black box. So today, the AI system is a black box. Okay? Is black box useful? Yes, it is. Do we really need to understand it? Of course, we hope so. But, if we don't understand it, is there a problem? Yes, there is a problem. But we can overcome it, okay? So let me give you a simple example, okay? So previously, I mentioned that for X-ray, the computer scientist, the mathematician, in fact, it was a bunch of mathematicians, okay? So the mathematician said, don't tell me how you decide whether this one has cancer or this one doesn't. Just tell me in reality after you have done, biopsy and all other tests, just tell me whether this person is confirmed to have cancer or not, okay? And here's the same thing. It's the input-output. Given a image, I know the output is yes, cancer, no, not cancer. Okay? And here's the same thing, okay? So essentially, everything we do, every decision we make is a function. It's a system, or what you call it a function, okay? What is a function? A function is you take an input, you put into a function, a system, whether you know this or not, and you come up with an output. Okay, so that's what we have. So here, mathematically, we have many functions. But here's a cat. You put in, you say, okay, I know it's a cat. Here, you put in, oh, I know it's a puppy. It's a dog. Okay? And so this one, you can see, is a bit more complicated than the usual function you are familiar with. Like if I put in a number, it give me a square of that number, or that number plus 3. Okay, that's a simple function. But here, you can already see that this is rather complicated. How do you describe why this is a dog? Okay, why that's a cat? I mean, can you explain in 3 sentences why it's a cat? If you can't, that means the inside animal identification function is actually very complicated. And indeed, it is very complicated. Okay? All right. Now, that one is a little bit easier thing. When you boil water, the boiling point is different depending on how high you are. Okay? And at the sea level, we know it's 100. But if you go to 1,800 meters, then become 95 degrees. And you go further up, it becomes 85 degrees. Okay? So there's actually a formula for this. But if you have enough of this data, you can actually figure out the formula. Not that difficult. Okay? It completely obeys certain simple physics principle. Okay? So this one, if you have enough data, you should be able to figure out an explicit formula. This will be a very simple one. Okay? All right. So let's look at the traditional way. How do we build a model? How do we build a function? Okay? We do the following. I mean, you guys, in school, you have experienced quite a bit. Okay? So traditionally, how do we do this? Given one input, I want an output. Given 6,000 meters, I want to have an output. Okay, so what do? You plug in a formula. You just go to a line to search how this is related to the altitude, the altitude. Then you get the formula. You just plug in, right? That's easy. That's what we call science. Okay, we have input-out function science. Many physics, all the physical laws, like the gravity. We have science. We have formula. Okay. And the other is a little bit more complicated. Let's do a model. Let's model it. Okay? Well, I use some polynomials, some linear functions, blah blah blah, to model it. So this is what we call modeling. The problem with modeling, you cannot have too many parameters. If you do, it becomes too complicated. Okay? So that's why never trust economists. Because they often, for this complex economics, they use 3 parameters it's just not going to work. okay? So that's why, modeling can be good, but sometimes doesn't work, okay? Okay, the other is approximation. We don't, we just approximate. We can never find the exact solution, but we say, okay, but let's do something that's close enough. That's called approximation. So we come up with a formula that's close enough, okay? And the brute force way is a listing. We list every temperature, or at least every temperature we care about here, and every altitude we care about, and every temperature there, we list it, and a little bit that we didn't cover, we use interpolation to do it, okay? So that's another way. And for the animal, it's the same thing. We just, list every possible animal and every picture. But you know what? You cannot list every picture because there are infinite many postures for cats and dogs, okay? So this is, not good. Listing, it works in many cases. In our government database, we have everything. In our university student roster, we have everything. You give me any student, I can tell you how he did in calculus, calculus 1, for example, right? So that's called a listing, okay? All right, so for 1,000 years, thousands of years, not 1,000 years, more than 1,000 years, okay? Mankind has advanced by understanding how this box works. That's science. That's what we call science. Science means, how does this box work? Okay? That's Newton's physics, for example, okay? That's chemistry. That's mathematics. Okay? So we often want to ask the question, why? Okay? So as if without understanding how the box works, it's not science. That's at least traditional, we all feel that. If you just tell me, a guy standing here doing some magic and he told you, if you are in, if you are, 4,500 meters high, your boiling point is, say, 85 degrees. And if you just sit there, you will say, is this guy a crank or some kind of charlatan or, a scammer? Because you want to ask him, how did you know? He said, well, I just come up in my head. Okay, I did some, you don't trust him, right? You want a formula, okay? But, and that's tradition. And I don't, So that has been a tradition, and that tradition has worked well for us for a long, long time, okay? And of course, if we really cannot understand, like economics, how economy works. I mean, just as I said, why Americans elected Donald Trump? If we can't, then we try to give 3 or 4 reasons why people voted for him. That's called approximation, okay? We use some simple things to approximate it. Okay? But let me just say that most systems in nature are much more complex than this, okay? So our effort to scientifically understand the box very often leads us to a very oversimplified, what we call baby model, okay? And just like the reason you heard, because the students, society today has defined gender by 97 different genders in the US. That's why people didn't like it. That's why people vote for Donald Trump. I mean, this kind of statement, oversimplification, okay? There are plenty of people who actually like the 90 plus genders in the US who voted for Donald Trump, okay? So it doesn't work, okay? So these baby models and the oversimplified system are usually inaccurate. And that's the least problem of it. They can also be misleading. So this is why, economic predictions are often wrong, simply because they're, by nature, they cannot be very accurate. If you just consider interest rate, employment rate, just a 3, 4 parameter, it's just not going to work, okay? And as I say, it can be harmful. If it's wrong, it can be harmful. Especially if it's wrong, people actually listen to it. Okay? So there was a famous study in the US trying to figure out what is the best investment strategy in the long run. You know, if you're going to invest in certain stock in sectors, whether you should buy, you should sell, it turned out, you know, by the way, do you know what was the result they found? The result was, for the last 70 years, the best investment strategy is to go against the predominant economic prediction by economists. Okay, if you just go against them, that's the best strategy, okay? So there are actually, maybe the model was not too wrong. Maybe you just take the opposite. It actually works, okay? Anyway, okay, so now let's come to the data-driven black box model. As I said, many things are too complex, like the cat and dog, okay? We don't really know what happened. Okay, so this is what we call today the black box model. That's what machine learning is about, okay? So it's not actually black. It's not like some magic or some witch, you know, or Ming, you know, these guys. It's really based on science, but the science is data-driven, okay? And it's mathematics. Okay? So you can view this as a sophisticated regression. What we call regression is data fitting, okay? Well, I'll show you some examples. Okay? And the process of figuring out exactly how this, what this black box should be is called machine learning. Okay? And you know, today we often talk about computer science. AI is part of computer science, but machine learning is actually first developed by mathematicians. Okay? You can go to the literature. It's a statistician named Vapnik who actually coined the term machine learning. And he actually wrote a book. It's a mathematician reading a book, and that is the foundation of modern machine learning. Okay. And interestingly, for almost all real-world applications, this black box model greatly outperformed the traditional so-called scientific model. Okay. Why is that? Because, as I said, the model was too complex to use very few parameters to approximate, to understand. And this black box model can have many, many more parameters built in. Okay? It's unbiased, and it's unemotional mostly. Okay? And today, because of the advances in AI, most scientists have also accepted this black model. So now, if you have something that's trained through machine learning, people actually accept it, even consider to be scientific. And people would even, oh, have you actually used data science to train a model? Okay, so now let me go back to, let me venture on something that you may have already known. That is, traditional Chinese medicine is being viewed as unscientific by many people in medical community because they didn't do, you know, this blind, double-blind testing. They did not have a molecular structure, DNA type of theory behind it. Okay, however, it works, especially for many what we call complicated disease, 疑难病. Okay, traditional Western medicine actually cannot solve it. But you go to a Chinese doctor, you know, from time to time, actually, often, it can actually solve the problem for you. Okay? I have many examples like this in, you know, I think. And why is that? Simply because, in fact, our body is a very complex system. This is agreed upon by everybody. Our body is a complex system. And traditional Western medicine also try to model the body into, you know, the blood flow, the bacteria, the you know, different hormones and everything, and that don't always. That's also a simplified model. Okay, so the traditional Chinese medicine is really data-driven, experience-driven, data-driven. Okay, so it does have some similarity here. Okay. All right, so now inside the black box, now we talk about the black box. What is in here? What is in here? Okay. Roughly speaking, we get a bunch of data to train, okay? So I cannot just give you a black box here, fill in the stuff inside. That's not gonna work. What it does, how does it work is you give me a bunch of input and output that's already known. And I want to fit the system, using the data you give me, okay? So, currently, which I'll get into more details, the most widely used data fitting system is what we call neural network, deep neural network. Okay, forget about that for a moment. Think about just trying to find a way to do it. Okay, so this is called what we call artificial neural network. Okay, and how does our brain work? This is the thing neuroscientists have been doing for a long time. Okay, so you look at let's say you really like sweets. Okay, so you look at something, immediately the certain neuron would fire up. So being activated. A few neurons don't get activated. So what are the neurons that get activated? That's those who look at it, say, reminded them something that's sweet. Okay, so get fired up. And if you enough of those fired up, then they continue to process those and trying to tell you in the end, decide this is some sweet goodie you want to have. Okay, so computer can simulate this process. So each circle here is called a neuron. It's an artificial neuron, and then each artificial neuron is a mathematical. Essentially, it's a simple mathematical function. Okay, and then we decide after we took this function whether it deserved to be looked into further, or in mathematical terms, whether we need to activate it. Okay, so there is a whole theory about this, and each neuron does very, very simple work, extremely simple. Just one, like we have many neurons tell me, oh, this is red color. It could be sweet. It just does this one thing. But the others say, oh, this look glossy, maybe look like sugar. It fire up. The other thing, oh, this shape look like a cake or look like a candy. It fires up. Okay, so all these combine to give you the information. So each neuron, but it's very simple, and somehow this works great. Okay, and it reminds me that I grew up in the Cultural Revolution time in China in the 1960s and the 70s, and there we have to learn a lot of the excerpt from Mao. And at the time, we just have to do it, right? We have to do this. But later on, I often go back to those. I found a lot of wisdom in which can be applied to neural networks, okay? So this is what, this is called 人民群众的力量是无穷的. Each 人民群众 is a neuron, okay? So if you put all these together, they can do big things, okay? Even though each one of them cannot do big things, okay? So mathematically, how does that work, okay? So I have input, output, okay? So this is think about these X-ray images. Yes, X-ray is X1. This image is X1. Y1 is cancer or not cancer. Cancer or not cancer, okay? So I have X1, then I have another one, I have blah, blah, I have N of them. I have a bunch of them, okay? So these are given input-output pairs I already know. Now, I want to fit a function so that the function takes an input and with the output, okay? Now, there are many, many functions like this, okay? So this is exactly what this machine learning is. You see, machine learning, what we call ML, is simply to find this f of x given the data we already have. All right. So how do we do this? Okay. So that's very simple. The mathematicians say, okay, let's consider each term is an error, right? I take the input, I give an output, which may or may not be exact. So if it's not exact, it's an error. Okay? So I want to minimize the cumulative error. I want to find the function that gives me the smallest cumulative error. That is exactly, just remember this formula. This is the foundation of machine learning. It's called the cost function, what we call the cost function, okay, or target function. Means we want to minimize. The cost function means the cumulative error is it's a kind of like the cost. I want to minimize the cost function, okay? So, and that is a foundation of machine learning. But the problem is, there are so many functions that do this, okay? And I'll show you some example, okay? So you don't want your function to be completely everywhere. You don't want this to be, to be all over the place. You want to restrict it to something that you can handle, like a linear function, a quadratic function. And why do we need to do this? You will see, okay? Or polynomials, for example. The problem, if we don't choose the function well, we could run into two problems. Okay? One is called underfitting. The other is called overfitting. Okay? So here's an example. Okay? Look at this data here. Okay? A bunch of data. Input is time. Value is, so the X will be the horizontal zone. The Y will be the vertical thing. Okay? So you can see these dots. You have a bunch of dots like this, input-output pairs. Okay? Now, you want to find a function that minimizes the cost, the error. Okay? So minimize this cumulative error here. Okay? Okay, you say, okay, I can only use linear function. I can use a straight line. Then what you get? You get something like this. This is the best straight line you can get. But is it good? No, it's not good, right? The error is still very large. And this is what we call underfitting. This is underfitted. It just means it doesn't perform very well. And you don't have enough freedom to make it good, okay? Now, let's look at the other extreme. I can use a polynomial. This will be like 15th order polynomial to approximate this. I did a perfect job. Okay, I did a perfect job. Do you think this is a good fitting? Because it looks artificial to me, right? And in fact, what happened is if you have new data, you will suddenly see this thing is way off. Okay, this is what we call the overfitting. And among those, which one is a problem? Actually, overfitting is a much bigger problem in machine learning. Because you have the freedom to choose a lot of parameters. We all know if you give me more parameter, more degree of freedom, I can fit everything. Right? But whatever you get is overfitting. Okay? It's not good. Okay? Now, a more sort of robust, probably a more suitable fitting is like this. It's not perfect, but it captures the spirit and give you some error. So in other words, you actually don't want to see this error become zero. Because if it's too good, it may not be, if there is a saying, if it's too good to be true, it is. Okay? Just some spam. So you don't want to have, this is an example. You have these two dots. You want to separate them. What we call a classifier. Let's say this is cancer, this is non-cancer. Okay? You want to find a curve that separates the two so that if you have a new dots coming in, on this side, no cancer. On that side, you have cancer. Okay? So if you try a linear thing, you can see you have a lot of errors here. It doesn't look good, okay? If you do, you can remove every error by having something like this. Well, it doesn't quite work. You can see this is definitely overfitting. It's not natural. However, if you do something like this, it probably works. And you are going to have a few outliers, errors here. But that's okay. Nothing is perfect. Even humans cannot be perfect. You're reading X-ray, often they make mistake. So you should allow this to make some mistake. Okay? All right. So overfitting, as I said, is actually it's a bigger problem than underfitting. All right. So how do you control overfitting, the behavior? Okay? So what we do in machine learning is to say, we still have this target cost function. Okay? We want to minimize the error, but we're going to put an extra term to force a better behavior of this function. Okay? So what is the better behavior? The better behavior is we don't want to see a lot of wiggling, for example. Okay? So we're going to put a term to force it to behave well. It's like in a school, a lot of teachers, we all go through this. We want the student to do really well in mathematics and in chemistry, in English, and we want cumulatively they all perform well. But we don't want to encourage the students every day to spend 16 hours, doing their homework, right? So we want to put an additional term called regularization. This is how government, regulations come in. Say, okay, in the U.S. or in Europe, you cannot study for more than, say, 10 hours a day. Okay? So we say, okay, you have to do some sports. You have to, hike some mountain or whatever, okay? So these are exactly the same principle, okay? We want you to minimize the error, but we don't want you to overdo it, okay? And this way, you create a very healthy target or cost function. And like what I say, this creates a very healthy student body. Same idea, okay? All right. So we can also do additional techniques to reduce overfitting, okay? And why we choose neural network? Because neural network tends to be much more stable, and it's easy to do to eliminate overfitting through something called the dropouts and the cross-validation. It's called dropout, which I don't have time to talk about in more detail. But it essentially says the following. It just says, I want to fit the curve here. I want to throw out a few. I just going to remove some of them. Then I do the fitting. Then I put this curve back to see how it works. Okay? If it works well, repeatedly after I remove some, refit them, then I think it's good. This is called, this is the idea of dropouts. Okay? And the cross-validation. Both of them are the same thing. Not same thing, but in fact, that's good because I want to. Neural network is a mathematical tool, first also developed by mathematicians, but it never found enough use before. Why? Because computationally it's more complicated. Okay, we don't have the computing power in the 50s. It was developed in the 50s. Also, we could not go very deep because typically, as I said about the suites, the neural network was very simple. Okay, but now we can go 100 layers deep. Later, I'll show you. Okay, so but I want to. I actually, instead for me to say this, I look at there is a video. Which I selected video, which is perfect because after it's done, it's time for a break. Okay.
My family and I visited Russia.
This is an advertisement.
Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get...
So let me just explain. Each neuron here perform a very simple linear function, linear operation. And then they come up with a number. This is from. Then you put some kind of threshold, which is which can be trained to tell as I said, for the sweet case whether this actually passes your sweet threshold. If it's not threshold, you don't activate. You just assume the neuron never fired. If it passes the threshold, it fired. Okay, so this is what this thresholding bias is about.
An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process...
Yeah, let me also explain. You can see the network made the wrong prediction. So then what happened? You already know, because of the wrong prediction, that adds up to the error. So when you cumulatively, when the error is too large, it will go back to modify these coefficients, these neurons, each stage, okay? Each of these stage, each process. Each one, as I say, is a linear function. So the linear function has coefficients, right? X 0.1 x1 times 0.5 x2, for example. But y is 0.1, y is 0.5. You need to go back to modify that. But how do you modify it? You modify it because you want to lower the cumulative error. This is called a gradient descent, or in this case, they use something called a backpropagation. Okay? And this is the process of training.
Assigned such that the network can predict the shapes correctly in most of the cases.
And it has to
this
go
brings
many,
our
many
training
rounds.
process to an end.
sometimes
You might
millions
wonder
run.
how long this training process takes. Honestly, neural networks may take hours or even months to train. But time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play, first differentiating the face from the background and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune. So, here's a question for you. Which of the following statements does not hold true? A. Activation functions are threshold functions. B. Error is calculated at each layer of the neural network. C. Both forward and back propagation take place during the training process of a neural network. D. Most of the data processing is carried out in the hidden layers. Leave your answer.
What do you think? By the way, all of them is true, except, as I say, the error is not calculated at each layer. It's calculated at the end, then back propagated. Okay, so this is the
Three of you.
It's yeah, okay. Right? It has more.
And foreseen by the big names. Companies such as Google, Amazon, and Nvidia have invested in developing products such as libraries, predictive models, and intuitive GPUs that support the implementation of neural networks. The question dividing the visionaries is on the reach of neural networks. To what extent can we replicate the human brain? We'd have to wait a few more years to give a definite answer. But if you enjoyed this video, it would only take a few seconds to like and share it.
Okay, so last time we stopped, after the video, you heard the word called hidden layers. Okay, hidden layers are the layers in the middle where you actually did all the work. Okay, so let me just say that the neural network is a concept that started way back in the 1950s, okay, and maybe even earlier. But at the time, we're really talking about a simple neural network like that. Input, output in the middle, there's one layer that does work. This is called a shallow neural network. And because it's shallow, only one layer, it cannot be that complicated, right? It's a very simple neural network. If you wanted to do complex things, what do? In one layer, you can still do it. You just increase the number of neurons in the middle. Okay, so you can do that, but the effect is, people. That's exactly what people did. Okay, people never venture into very deep neural networks. Why is that? Okay, why we were just so happy with the simple neural network, 1 to 2 layers with many, many neurons, okay? Or maybe not even that many neurons. I'll tell you why. Because mathematically, we cannot analyze neural networks that goes beyond 1 layer. Even for 2 layers, it becomes more complex. You can still do something. But if you go beyond 2, mathematically, it's impossible to analyze. We cannot prove theorem. That's why mathematicians never ventured into deep neural networks, because they never thought they need to go to deep neural networks anyway. And also, there is no computer that has enough power to go that deep. Okay? All right. So everything changed actually before 2012, but really the revolution started in 2012. Okay, so there is a I don't know. You remember earlier I had a picture, cat, dog. You want to analyze this black box in the middle, right? So this is called a ImageNet competition challenge. Okay? Why they want to do this? Remember, for a long time, you can Google something. You can Google, say, give me a picture of a tree. The Google will come up with a bunch of photos of a tree. Do you know how they did it long time ago? Let's say more than 10 years ago, 15 years ago. Because people manually label those as trees. They put something called a tag. Okay? So when you upload a photo, you say, okay, a tree with beautiful, foliage, for example, okay? Or this is a pine tree, or this is, an aspen tree, whatever. So that's why Google can do the search and come up with these pictures, okay? But we all know this is unsustainable because we have so many more photos, including artificially generated photo. We don't have the manpower to do all the tagging. So in the around 2010 or maybe 2009, so one of the scientists, professors in Stanford University, she's very famous, called Fei-Fei Li. Okay, it's a Chinese. She was born in China, and she became a very famous, very well-known professor in computer science. And she started this ImageNet challenge. Okay, so what she did was to, using crawling to obtain a database of over 10 million images. 10 million, okay, that's a large number of images. Each one it's like a cat, a dog, a tree, a car, a plane, and blah, blah, blah. Then she did have manual label. Okay, so she, all these were crowdsourced. So, if you label a few, they pay you a few, a few cents. And in this, in Hong Kong may not mean much, but if you go to Bangladesh, that's a lot of money, okay? So, you get people all over the world to help labeling that. Typically with 1 or 2 people, then you can cross-check to see whether they did it right. And then, with this database, there was a competition she started saying, see who can automatically, using a computer to label them, to generate label tag that are most accurate. So for a long time, Google actually, before this work in 2012, Google had the best result with about 50-some success rate. It doesn't really say, you have, it's a cat. It gives you probability, or a dog. It say with 0.4 probability it's a cat, with 0.3 probability it's a bear, and with 0.1 it's blah, blah, blah. So you can, for top 3, okay, so you can say either one of the top 3 is correct or the top 1 is correct. The top 1 probably is much lower. The top 3 is maybe 60% or so, okay? And many of them use different techniques, use neural network, more like these kind of neural network, okay? And or using other machine learning techniques like support vector machines or your random forest. All these are machine learning techniques developed by mathematicians, computer scientists, okay? Until in 2012, a team in University of Toronto, the most famous person is Geoffrey Hinton, okay? He is widely considered to be one of the godfathers of AI. And he actually won the Turing Award for various work. And later, I will show you he actually won the Nobel Prize this year, okay? And so they actually, they have in there with AlexNet, there was a tremendous jump to something like 70-some%, because they employed a deep neural network to do it with, I think, 11 hidden layers instead of 1 or 2. Okay? And they also used something which was not their invention, but nobody knew what to do with them, called the convolutional neural network, CNN, okay, which I'll explain also. And that just really significantly elevated. And then people start to use deep neural networks to do this challenge. So we even see neural networks like a ResNet with well over 100 hidden layers. And gradually, soon, the accuracy have been raised to over 90%, 98. Today it's very accurate, okay, for these kind of image labeling. And that actually started this deep neural network, deep learning revolution. Okay, so what is deep learning? Deep learning simply means you have a deeper layer, many hidden layers. Deep, the many layers. That's called the deep learning. Okay, so deep neural network and deep learning. Okay, so what are some of the applications? Actually, you may want to ask the opposite question: which AI platform does not use deep learning? The answer is almost none today. Okay, but at the time it was a revolution. Okay, so because of that, if you look at this year, it's very, very interesting. The Nobel Prize in physics is, guess who? Geoffrey Hinton. And along with John Hopfield, who is also founded this, you see how the foundational discoveries and inventions that enable machine learning with artificial neural networks. Okay? They are given Nobel Prize in physics. They're not physicists at all. Okay? Now, what about chemistry? See these three guys? They're all from DeepMind, the Google's DeepMind. They did this, this is the guy, Demis Hassabis. Actually, his mother is Chinese, okay? He was the guy who did AlphaGo at DeepMind. And they created, after AlphaGo, these guys created what were they called AlphaFold to predict the protein structures, which were originally, scientists didn't know how to do it. They used a very complex molecular dynamics model to do it. It took a long time, and sometimes because it's highly unstable, so, after a long time, it may not be accurate. So they developed the AI tools using deep learning to actually revolutionize the, the protein folding, okay? Okay, so here's some of the example I talk about. ImageNet, I just talked about. AlphaGo, okay? So it was also first developed by DeepMind, where Demis was also the chief, the chief architecture of AlphaGo. And we know that AlphaGo had beaten Lee Sedol, who was the sort of the champion Go player, a feat that people thought it would never be able to achieve using AI, but it did it. And in fact, not only it did it, so AlphaGo was able to outperform champion Go players by learning the playbook, the examples of Go from thousands, tens of thousands of Go, actual games. It learned to play. So just very shortly afterwards, they actually developed something called AlphaGo Zero. Why is it called AlphaGo Zero? Zero means it never used any human knowledge anymore. It just got rid of human knowledge. It just trained by itself. Left hand versus right hand, essentially, okay? And soon it became, it became so powerful that it just completely annihilated AlphaGo. So AlphaGo 0 today, no human player could come even close to AlphaGo 0. It's impossible. Okay, so you can talk to all the best players in the world. Nobody come close to AlphaGo 0. So what the top players do today? Do you know what the top Go players do today? They train using AlphaGo 0. Okay, so the best player today, the professional players they look at similarities with AlphaGo 0. What that means is, if you want to make a move, given the current board, you want to make a move, then you let AlphaGo 0 also make a move. And you see how many times your move is the same as AlphaGo 0 move. Okay? And the top professional players hit roughly 67 to 69%. The best player, currently the number one player in the world, I'm not a Go guy, okay? I know this young Korean prodigy. His rate of, his matching rate with AlphaGo 0 is 73%. Far exceed, significant, I wouldn't say far, significant, because there are a couple of Chinese players who is also in the 70s, like 71, 72. So that's why he's the number one player in the world, okay? So now every Go player, if you want to be number one, you train with AlphaGo 0, okay? All right, now face recognition, you go to airport today, many of you have done, you just go there, I don't have to take out my ID, look at me, and open the door, and that's face recognition technology, and it's very mature today. Okay, it's this has been going on for a long time until deep learning comes in. Now we have 99.99 type of accuracy. Okay, and protein structure, I already say AlphaFold, and this is just 4 of the examples. Okay, so remember we talk about the work of remember the Jeffrey Hinton we called convolutional neural network, right? CNN, convolutional. So when you talk about convolutional neural network, I want to ask you, how many of you in school have learned something called a convolution? Anybody? Have our teachers, have we taught convolution in school? Okay, so convolution, let me give you a simple idea. You have stock price, okay? Every day you have a price. But sometimes, it fluctuates too much. So you want to take an average. But you don't want to take the whole thing, give you one average. So you take a little bit of window. You say, okay, average for the past 3 days is one thing. Then you shift one day, you get another average. Then you shift one day, you get another. It's called a moving average. That is convolution. Okay, so let me give you a simple illustration. What is convolution? Okay, so let me look at here. So this thing here is what we call a filter or a mask. And here is the data. It doesn't have to be like this. It can be, both can be very big, okay? But typically it's one small window or small filter, one big data. So you take the 3 by 3 and you just multiply the element together and then add them up. Does that make sense? You see here? See here you take these together. You add up to 4, okay? And then it just shows it. Let's take one more. 4, 3, and you see this color, right? It moves. It's like a moving average, except the average are using this mask here, or these coefficients. This is called a convolution, Okay, so here is an example I actually produced. You can see, again, I'm using exactly the same window. Okay, same mask or same window you call. And when I move to this part, okay, you can see you just multiply the corresponding element together and add them up. You got 4. So 4 is over there. You see in this box, 4. Okay? Now, why it's the 4th? Because the first one is the top left 3. Then you shift by 1, you shift by 1. You shift 4 times, you got to this box. Okay? That's why 4 over there. And that's exactly what happened. You do for every one of them. You can move, because that is 3 by 3, so you actually get only a 5 by 5. Right? Okay, so if you change this box a little bit, okay, change this box, you see, again, for this, okay, what I do is 0 times 1. 0 times 0, 2 times 0, I got 0. But here I have 3 times 1, plus 0 times 1, plus 0 times 0, that's 3. And then I have 1 times 1, 0 times 1, and 1 times 1. Add them up, I got 5. And that's this number 5. This is convolution. This is called a convolution. Okay. Okay, so convolution neural network means the following. All the hidden layers, these neurons, remember neurons we say doing linear, simple linear operations? Okay? Each one of here is a linear operation, right? Just multiply coefficients together and add up. That's linear, okay? And the convolutional neural simply means these linear functions in the hidden layer are convolutions. Why convolutions? I'll explain, okay? So, you think, oh, why we do convolution? What's the advantage? Well, you will see, okay? And you typically see a figure like this for the convolutional neural network. This one is a specific one for handwritten digit recognition. And then you see, so you have like 32 of 28 by 28, okay? So you have, it just means how many, so you have, go back here, you have how many of windows or filters like this, okay? So there you have 32 of them. Here it say you have 32 of them we use, and each one is 28 by 28. Then here we have 32, but 14 by 14, and there we have 64, then 64 7 by 7 convolution. Okay, so it's just a convolution. Okay, and once you pass through the neural network, in the middle you have these so-called activation function, which I explained. If it doesn't pass through some threshold, we just set it to 0. And typically we use something called ReLU. This is L, not an I. Okay, this is a L, called the ReLU function. It goes like this. If you return a positive value, we keep it. If it returns a negative value, we keep it set it to 0. We don't activate. Okay, not activating means we set it to 0. Okay, so that's why it's called activation. And the ReLU is the most frequently used activation function today. Okay, there are many others. It doesn't have to be ReLU. Okay, but there, this is the most most frequently used activate, and it's typically because it performed really well. Okay, all right. Why GPU? Have you seen the news? Jensen Huang came to HKUST, even went to a place to get some street food, right? Received in my university, receiving the honorary doc. And you also saw at least a few days ago, NVIDIA overtakes Apple as world's most valuable company. Why? You know what it makes? It makes something called a GPU. Right? GPU, graphics processing unit. When I ask you how many of you have learned, have performed convolution, nobody raised hand. Okay? But if I ask you how many of you have played any game, I'm pretty sure you don't. How many have not played any game? Raise hand. Teachers, please pay attention, okay? None, right? So you all play the game, and you all know when you play game, you have to use GPU, right? So this graphic processing unit, okay? Now, let's look at comparison. Why GPU? What is GPU? What is CPU? Okay, CPU is called the central processing unit, right? Our computer, our laptop, use CPU, Intel CPU, or and we often hear about supercomputers. That right? Supercomputers. Okay. The most powerful supercomputer in the world today is called the Frontier. It's a U.S. Developed supercomputer. Japan also has a bunch. China has a few. But right now, the champion is Frontier, developed at Oak Ridge National Lab in the U.S. Right? It has 8.7 million cores. Okay? So each core is an independent processor. Okay? Now, you have 7 million cores, 7 million processors that can process data at the same time. For example, you have a bunch of tasks. One say you have to perform adding these two numbers together. The other say, I want you to square them together, then multiply them together. Okay? So, but each core can do this kind of thing for you. So it has a massive parallel capability. Okay, this is the most powerful CPU in the world. But what about GPU? Okay, you all heard NVIDIA H100. That's the one that used to train GPT. Actually, we don't know for the current GPT-4 and the large language models. You know how many cores one GPU has? One NVIDIA 100? It has 18,000 cores. Just one little GPU, okay, with this many cores. So when we do AI, we typically let me just say for GPT-4, for the current large language, typically they use over 10,000 GPUs H100 together. So if you add 10,000 GPUs, how many cores are you going to have? You're going to have 184 million cores compared to the supercomputer, only 8 million cores. So does that mean if I put 100 or 10,000 GPU together, or H100 GPU together, is it going to be much more powerful than supercomputer? Well, not necessarily, okay? There is a difference between one core here and one core there, okay? The GPU cores are much less powerful than the supercomputer CPU core. However, what's the difference here? The difference, but they are, GPU core can also do multiplication, subtraction, addition. What's the difference? The difference is like here I have, a row of processor or row of soldiers. Okay, if I'm using the comparison of CPU and GPU, let's say in the CPU case, each one of you, I give two numbers in front of you. Okay? Each CPU can do the following. Each CPU core can say, right, you do addition, and Stanley, you multiply them together, okay? And you can say, each one can say, okay, you can do the square root of one of them, multiply by the square of it, or adding the square. You can do all these kind of things independently. But if in the GPU case, I have 100 million of them, well, not 100 million, you can divide them into two things, okay? Let's say I have 1 million cores in front of me. I have these two numbers. They can only do one thing at the same time. They have to do the same thing. They can only add the two numbers together or multiply them together. Whatever command you give them, but they have to be exactly the same. Okay? So this limits the usefulness of GPU cores. You have to design your algorithm to make sure that you can take advantage of this many cores, like 100 million cores. Okay? So now you know why you do convolution. Let's look at the convolution. You see, convolution, you do exactly the same thing. You move this window to the next spot, but still do exactly the same thing. You multiply 2, in this case, you multiply 2 to this, 0 to that, and 3 to here, and 1 here, you add them up. That's exactly the same thing. For each one of them, you do the same thing. So they're perfect for GPU. Okay? That's why GPUs are now used for AI training, and that's why we use convolutional neural network. Okay? Without the GPU, because the data is so massive, even 8 million cores are not enough. You really need to have hundreds of millions of cores. Okay? This is why NVIDIA has overtaken Apple as the most valuable company, because everybody realized if you believe AI is going to be the future of our society, of our daily life, is going to be the future of everything, you need GPUs. Okay? So I'm sorry I missed out the opportunity to buy some NVIDIA stocks. I'm not the only one. Remember this guy, Sun Zhenyi, for SoftBank? He bought them at $7, and he sold them at $2, okay? So I think he's the one that's felt really bad about it. Okay, all right. I'm going to use the remaining 20 or so minutes to talk about the rise of modern generative AI. Okay, so really the revolution started with the transformer architecture. So previously we do so-called natural language processing. We cannot we cannot process all the text together. We process them sequentially. So what happened is when you don't look at all the words together, you tend to forget. There is some example I want to show you, okay? And then until in 2017, there was a paper called Attention is All You Need by a bunch of engineers from Google. And there they introduced something called a transformer, which is just a mathematical way of embedding words, or what they call tokens, don't have to be words, into a mathematical space. Okay, so that started all the large language model revolution. And that's, but this is not started, but this is viewed as the most important development for generative AI. Okay? But before that, there was something for image generation. It's called generative adversarial network called GAN. Okay? Which also took the community by storm, and because of that, you were able to make these computer-generated images. Okay? In fact, many of you know this platform called Midjourney. Midjourney used GAN to generate the images. Now it uses something else, which I'll talk about. Okay, so so let me give you. I want to focus on GANs because mathematically it's very interesting. Okay, so this is a picture called Edmund de Bellamy, sold in 2018 for actually 400,000 US dollars. It's a big, sold for a lot of money. And if you look at this picture, there is a signature here. You know, this is where artists put their name there. Well, there was no artist here. The signature was a mathematical formula. This is how math comes in, okay? It's a mathematical formula. And why? Because this is exactly the mathematical formula for GAN. Okay, so this is and I probably don't have time to go into a lot of details, but let me give you the generative AI is getting, even at the time, there are so many things happening. This is a piece of music. It's completely generated by AI. I want to fast forward to. You can see it's pretty good. Yeah. So these are, there's a website called These Faces Don't Exist. These are artificially generated, AI-generated images, faces, look very real. Okay. Now, in fact, we all know, some Jimmy Lai, we all know this. So there was an article on New York Times talking about President Joe Biden, his son, Hunter Biden, got into a lot of trouble, right? And it turned out that some of them are real, but some of them appear to be fake they quoted a guy named Martin Aspen, this guy, about what Hunter Biden had done. And apparently, Jimmy Lai was behind this. Okay, this was fully generated by AI. So New York Times actually had a very long article about this whole thing. Okay, so you can see AI, even at the time, people didn't know. A lot of people were not aware. Many images you see today are. We know that it's AI, okay? Because I have even received threatening emails saying, we have an image of you in a hotel with a woman, and please give me, $1,000 US. You probably received that too, okay? And it was clearly done by AI, okay? So let me just explain what is GAN, okay? In fact, this is almost the sort of the math. It really proposed a let's say I want to make Van Gogh images. Okay, so I have Van Gogh. Okay, you can, if you want to get a Van Gogh image, you can go to Shenzhen. There was a place called the Dafengchun. Okay, you can ask one of the guy to imitate Van Gogh Starry Night, and the guy is very, very good. He can do it in like 30 minutes or so, okay? But, that's imitation. But let's say if you want a image, a picture that looks like Van Gogh. An expert may actually think it's a Van Gogh, but they've never seen before. Then you can make a lot of money. In fact, this also happened, okay? So one way to do it is, this is exactly the problem GAN is trying to address, okay? So how does it work? It's mathematical, how does that work? I showed you the formula, but I don't want to go into the detail of the image, because I'm going to bore some of you. However, I want to give you the basic ideas why it's called a GAN, okay? GAN has 3 words: generative, adversarial, networks, okay? One is generative, one is adversarial, the other is net. So what does that mean, okay? Generative, we all know. We just generate these images, okay? Like these are all computer-generated images. That's easy to understand. But why adversarial? Okay, I'll give you an example. Adversarial serve as someone who keep you honest. They try to criticize you. Oh, your painting is terrible. It's like your teacher, okay? You do some homework, the teacher says, no, this is wrong, right? This is adversarial. It's like someone who critique you, okay? And who serve as a critic, a reviewer, a teacher, or in Chinese we say 早茶, okay? Just, it didn't like you, give you 早茶, okay? And the discriminator's job is to find, what deficiencies of the generated content, okay? So they play this game, okay? So here is an example, how does that work? And all these are put in that mathematical formula, by the way, okay? So let's say I give you a bunch of images like this, okay? I want you to generate something that look like this, okay? Think about these are Hong Kong dollars bills, and you want to fake these Hong Kong dollar bill, okay? So you made your first batch. You look at those. Tell me, do they look like this? Your teacher look at this, say, this is bullshit. Okay, this is just, the color is wrong. Okay, the background is not right. Go back. Okay, so you learned the lesson. Teacher didn't like it and give you some ideas. Okay, you went back. You changed the background. You say, oh, now the background looks great. It's the same. But the teacher said, no, this is terrible. Can't you see the color of the dots is not the same as this? You say, oh, yeah, maybe. Okay, that's not right. So now you learn. You go back, it's being rejected, so you come up with this. Now tell me what's wrong with, does it look like that? It doesn't, right? So where was the problem? Can you immediately see? Well, you see that all the picture here have exactly 10 dots. But here you have 11. Am I right? You have 11. So the teacher, it took a while for the teacher to say, I don't think, even though I don't think it looks right, but let me see why it's wrong. So the teacher said, no, you got one more dot. Okay? So then you go back, you fix it. You fix to something like this. 10 dots, background color, foreground color, everything is correct. Is it good? It's not good, okay? Still it's not good. Why it's not good? So tell me, why is it not good? You just don't think it's good, okay? Because the location of the dots, okay? These are more centered, right? These are more randomly, everywhere else. These are more center random. This is more uniform random. And sure enough, because the position of dots were obtained using a Gaussian normal distribution. This uses a uniform distribution. This is a little tougher, but you still learn. So you play around with the position of the dots, okay? And finally you come up with this, and the teacher look at it and say, great job. Okay, so you see after rounds of this criticism, you generate the discriminate, your teacher say no good, then you go back, you regenerate, the teacher say no good, and back and forth a few times, you come up with a good one. That's GAN. That tells you. So you have a discriminator, you have a generator, the adversarial is the discriminator. Okay. And so this is called growing up together, okay? You just, so there are certain conditions you have to satisfy for this to work. One of them is the teacher has to be very constructive. If in the beginning you have, you did a terrible job, the teacher just summarily dismissed you, say you're no good, just go back. It didn't give you any constructive feedback. You cannot make it work. Or if you already figured out, got so close, the teacher have no clue even where to look for your deficiencies, it's not going to be to work either. But usually it's the first case. The first case, the teacher is not very good. You are pretty good, and the teacher could look at it, and he or she just didn't bother to look for details and just let you pass. It's too loose. Every student who did mediocre work, the teacher say, you're good, you're good. Then you are not going to be able to grow. Or the teacher is too strict. Keep saying you're no good. That's not going to work, okay? So imagine, a teacher is a very strict teacher, but you have a student who is not very, talented, but also has a very strong pride. What's going to happen? It's just not going to produce a good. The other way is not working either, okay? So that's why GAN also teaches us how to do it in school. Okay, actually the Chinese leaders have known this philosophy for a long time. I also, as I mentioned, Chairman Mao expert, I learned to dig them up. So this is what they call, this is a 在斗争中学习，在斗争中成长。Okay, you have this adversarial, generation rejection, generation, discriminator, fighting, and together both of you grow. Okay, so this is the philosophy that you can find among the modern Chinese leaders. Okay, and this was. I discovered, so I was looking for these, and I found exactly this, which tells me, which was almost like a carbon copy of the philosophy of GAN. Okay, so how does that mathematically work? Mathematical work is you start off with something that is completely unlike what you want to generate. We just start with a random noise. Then we pass through a function called the generator. Okay, you can do this. Okay, you can prove that you can always find the function g that turns this into that. The only problem is, what is your g? Well, didn't we say everything can be approximated using neural networks? So we use a neural network to approximate this g, but of course we have to train it. That's why we have a lot of trained data. We're going to train the g to do this. And to train the g, we need to have the discriminator to tell us why this g is improved, how the g should improve. And this discriminator is also a function. And we use neural network to approximate. So just going this back and forth using neural network, we continue to modify the neural network's coefficients training, and we obtain what we want, okay? So I'm going to skip this, but this whole thing is exactly about what I told you, except in a very sophisticated mathematical term, which I don't think I want to go into details, okay? So essentially, let me just try to say the discriminator tried to tell you your work is no good, but constructively. The generator is trying to convince the discriminator, your teacher, that my work is good. And whenever the teacher feedbacks some information, it takes back to improve. Okay? Through this process, we actually train the neural network. Okay? So basically, as I said, I'm going to skip. So both the generator and the discriminator, the students and the teacher, are modeled by neural networks. Okay? Actually, everything today in AI is modeled by neural networks. Just remember this. Okay? So this is the general architecture, which I already mentioned. You can see it's exactly what I mentioned. You do need to have a lot of training data, okay? What is the real thing? You know, you need to have, let's say if you want to do the Van Gogh image, you really need to have a lot of Van Gogh images, okay, to train for success. And training is very, very difficult, okay? As I said, we're trying to make Van Gogh a new Van Gogh, not an imitated Van Gogh. We try to make a new Van Gogh that looks like Van Gogh, but people have never seen before. Okay? This is how you make money, right? If you want to, you discover new Van Gogh, okay? And mathematically, we solve this problem using GAN through something called a divergence, which I'm not going to mention today. Just remember, the underlying principle is all mathematics. Just remember, okay? Okay, so what could be the problem? The problem is also very often, it's actually very difficult. So what happens is sometimes we have something called a vanishing gradient. Vanishing gradient means the teacher can no longer give you any feedback, even though you may not be at the best. So if you give something, the teacher has no feedback or no valuable feedback, that's called vanishing gradient. It just, the gradient means the slope, okay? You have no way to, you don't know which direction to go. A typical way of finding the optimal is along the slope. Let's say you want to reach to the valley, you go the steepest route you can see. But here I'm standing something very flat. I have no gradient. So I have no clue where do I go to get to the valley. And if your teacher is like this floor, it doesn't give you any feedback, you have no way to know what's next. So this is called a vanishing gradient. The other is, this is something like you actually got stuck in a local minimum. And sometimes a couple of local minimum, and it just, it's not optimal, but you just cannot jump out of it, okay? It's like the teacher give you, a direction that sends you to something, then the teacher wasn't sure whether this was good, give you something else, you move to another direction, but then the teacher said, well, I think maybe that's the previous was good, and got into this cycle, you'll never be able to improve. So it just, circulating among a few non-optimal solutions, okay? So these, but anyway, so all these can be solved, okay? That's why, so you can use GAN to generate a lot of sample like this, fashion sample is generated by here. And this is a very famous one called CIFAR-10 database. And using the CIFAR-10 base, you can generate, train again. This is all being very well trained, okay? You can generate a lot of things that look like images in here. These are the celebrities. These are celebrity images. And using that, you can also train to generate human faces from the celebrity, okay? And you can generate this enemy images, okay, using GAN. All these are done. These are portraits from oil paintings generated, okay, and so we can do very high resolution human faces, okay. So these were all generated by AI, okay, and this is an image that won grand prize in a digital art competition. And this was generated using Midjourney, which will use GAN, okay? It won the grand prize, and people didn't know that when he won the prize. He said, oh, actually, I did it using AI, so there was a big controversy, okay? So, this is something I did using GAN myself. I inputted this image, and I come up with an abstract. I was very interested in abstract painting. This is something I would say it's quite interesting. Let's put it that way, okay? And so well-known project using GAN, Midjourney, as I say, NVIDIA Clara, that's a healthcare platform, and also deep fake technology. You have these fake videos, actually use GAN, okay? And Cosmos studies using study of dark matter, that's using GAN. Okay? And now I want to do my last one, that is ChatGPT. Okay? That is a milestone, really, in the generative AI revolution. Okay, so you can see now, with ChatGPT, you can do a lot of stuff. You can have dialogue with it, and it's called the pre-trained transformer. Okay, generative pre-trained GPT. Okay, so just give you a quick rundown of what happened. It actually was not something that's immediate. In fact, it started off by GPT-1, GPT-2, GPT-3. And you can see the parameters. That means the neural network become larger and larger, okay? So when you hit GPT-3, it's 175 billion. And the training data size, it become 570 gigabytes, okay? And ChatGPT is GPT 3.5, uses exactly the same training data, but it added the interactiveness. So that revolutionized, or at least was a big milestone for its first large language model, okay? And of course, since then, it just became extreme explosion, okay? So the GPT-4 today use 1.7 trillion parameters. That's an estimate, okay? And how much data used? This almost like, it's secret, but I saw somewhere saying about 10 trillion data. We essentially use every data we could use, so we have no more data. We exhausted the existing data, okay? And you can see this is the development of various. There are a bunch of Chinese ones. The first one, Chinese one, was made by Baidu called Ernie, okay? Now you have like 100 Chinese large language models, okay? So transformer is really the game changer. As I said, I'm not going to go into details here, but just keep in mind that it can learn long sentences and knowing the logical relation. For example, okay, attention mechanism. So the cat sat on the mat and it purred, okay? And here, the book I read yesterday was amazing. It has such a great story. For a long time, we could not figure out it means the book. But in the transformer model, this was very easy because look at all the text together. It became very easy. And that's why with the transformer architecture, the large language training together with neural network actually became possible. Okay? And here is how things work. Just give you an example. How this is GPT-3, okay? So today the weather is not. Then there are words that can make sense. It's not bad, it's not good, it's not great, it's not armed. Clearly that's not possible. So we give a 0 probability, and if it's not bad, we give 0.2. It's not that. That's possible. It's not that great. Okay? So, but it's small probability. We give 0.05. It's not good. It's probably the highest. It's not excellent. We probably don't say that. So we give a possibility. And this is, repeatedly used. I mean, this is a famous, poem by, Tom Poem. And you can see that it just keeps generating the next one using a probabilistic model. So you want to say, okay, if I have the GPT is because good has the highest probability, am I going to generate today the weather is not good? Well, not necessarily, because if you do this, then everything is fixed. But when you play with ChatGPT, you know every time you get a different answer. So it doesn't actually take the one with the highest probability. It select one with high probabilities. So it could be good. It could also pick bad. It could also pick that sometimes, depending on how you allow this, okay? So this is why you get all different answers each time you use ChatGPT because of this. Okay. And you can see how many data is being used. But I do want to say that Chinese constitute a very small percentage of ChatGPT, less than 3%. Okay, so we need to, we need to develop Chinese language, large language models who can use a lot more Chinese data. Okay, and this I'm going to skip this. Today there is something called a stable diffusion. And stable diffusion is almost all the images today are generated using diffusion, okay? And it superseded GAN. How does that work is you first add noise, okay? You first add noise, then you reverse the process by called the denoising. But adding noise is something called a diffusion. It cannot be reversed. It can locally somehow reverse. So as you reverse it, you are going to get something completely different, but within the framework, okay? So that's how stable diffusion works. It just takes something, completely turn into random noise, then you reverse the noise, you'll get something that's different from what you inputted, but also in that general category, because you did some training. That's how diffusion works. Now, almost everything, imaging, video, generally use the diffusion model instead of the GAN model. But a few still use GAN, okay? And these, and my final slide, these are some of my final thoughts on AI. What's next? I think AI ethics is going to be a big topic today. Whether we can survive with AI, whether it's going to create social problems for us, okay? And there are many others. Science, AI for science is, again, a frontier today. It's one of the hottest frontier. Can we solve math problems using AI? The answer is not so great today, but soon it will be very good. Can we discover new protein structure? Yes, we have already been doing this. Can we actually discover new physics? Yes, we are already working on this, okay? And a bunch of others. But the pinnacle is what we call artificial general intelligence, AGI, okay? It's just like a human intelligence. Maybe, if you listen to Sam Altman, you listen to Ilya, they say this is, possible, and they're going to be 10,000 times more smarter than human, which I think is a very scary thought, okay? And I think that's the end of my presentation. Thank you very much.
Thank you for Professor Wang's wonderful presentation. I believe everyone has been inspired by his talk. Now, it's time for the Q&A session. If you have any questions for Professor Wang, please raise your hand, and our staff will bring you a microphone. Who would like to ask the first question?
By the way, I do want to say one thing. People ask me in the era of AI, what are the most important skills? Okay, so AI can do a lot of things. In the end, it's really those who can use AI that will be the winners in the society. Who are the people who can use AI the best, the best, okay? These are the people who can ask questions and who can discriminate the results are good or bad, okay? So asking questions is actually one of the most important skills in the future, in the AI future. Unfortunately, this is something we don't teach in our school. Stanley, we need to do something. Okay. Yeah. Huh? Anybody?
Professor Wang, what do you think about how AI change students' learning, the model of students' learning?
Okay, this is a very good question. There was I give you one example. There was a book called Alice Sparkle, if you go to Amazon, you will find this book, and it's actually sold pretty well. So, so the author is a guy, Rishi Amari. He's not an author. He's not an artist. So this book was a children's book with 12 illustrations, and accompanied with each illustration there was a little bit of story, right? And he did it in a single weekend. Why? He used Midjourney to draw all 12 figures, and he used ChatGPT to write the story. Okay? And then he published it in a weekend, on a weekend, and it sold pretty well on Amazon. So this is the next wave of learning, okay? So the learning is about using AI. You know, our schools sometimes are so concerned that, you know, we use AI, you know, students will not learn the basic writing skill and blah, 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 which has a good point. I actually think it is a concern. However, it's just like when calculator first came out. You tell the student, you cannot use calculator in class. But guess what? Everybody was using calculator, you know. And now we learn to coexist with calculator. And I think we're going to learn how to not only coexist with AI, but turn AI into tools for learning. And so my belief is in the future, we will see a complete overhaul of curriculums and with much more emphasis on using AI as your co-pilot, as your learning tool. We have more project-based learning. I'm using that example. I asked my kids to do a book. I think this will be a great learning opportunity. You have to learn how to draw. You have to come up with a story. That's your imagination. You have to, prompt the AI to give you the right image. That's asking questions. If you don't like it, you have to tell, So all these are important part, and that's why, in the U.S. we have very well-known schools like All-In College that does project-based learning. It doesn't teach you, calculus on Blackboard. It gives you a bunch of materials. Say the first class, you make a boat with that material I gave you. Okay, project-based learning. With AI, I think AI is going to be your mentor. It's going to be your teammate. It's going to be your co-pilot. And we can really think about project-based learning based on AI.
Thank you, Professor Wang. Are there any other questions?
Oh, yeah. We have...
I'm sorry, Professor. So, will AI be able to understand human emotions in the future? And how?
Okay, great
Thank you.
question. Okay, thank you, thank you. Today, I think one thing is lacking with AI is it doesn't display the kind of emotion, humans display. In fact, you all know there's a Turing test, right? You have a dialogue with whoever behind the scene, and you want to see whether this machine can fool you as being a real human. Okay, so there are a lot of people think ChatGPT, especially GPT-4 or some of the other large language have passed the Turing test. But one thing they haven't passed is they hardly display any emotion. So from there, you can probably guess it's not a machine, even though this part that people are still working on. And the other part that, to be honest, some people also, teacher told me, I can easily see this is written by ChatGPT because it's so much better than our student can write. Okay, so but I think everybody now is working on the emotional side. I think it's just a matter of maybe 2-3 years. We are going to be able to see AI possess human-like emotion. It's not easy to do, but it's also not as hard as we think. So that's my prediction, okay?
Thank you, thank you.
Yeah.
Thank you, Professor Wang.
Yeah.
So will there be a problem if there's not enough data for the AI to continue to train? Because as AI advances, there's more data needed to train the AI. But will there be a difficulty to generate enough data for them to train?
Wow, this is incredibly a good question. I actually been asking this question myself. Today. I saw a video by one of the co-founders of OpenAI, Ilya, who is a very famous persona today. He left OpenAI. He essentially said, we have exhausted all the material, the training data we have for large language model. There wouldn't be any more data, okay? So then here comes an idea. How about we use machine to generate data, and then we train using the machine generate data, right? Is that a great idea? Okay, let me tell you something. Okay. I think a team in Stanford University published a paper in Nature. It did exactly this. It trained a language model using the data generated by AI, and then feed it back, uses those generated as training data and training again, okay? Remember, years ago, there was something called mad cow disease. Remember this, okay? This was, cows are fed with carcasses, basically food created by the dead cows or sheep. And so it created this mad cow disease using this process. So this is what we call the AI mad cow disease. You use the data. AI, ChatGPT use a lot of Wikipedia because, so you can see a lot of the ChatGPT articles was written like Wikipedia. So guess what? People today, when they create the Wikipedia page, they use ChatGPT to generate that page. And then the next iteration, they take that again, feed into the system. So Stanford professors, scholars actually did a study, and they discovered after 7 rounds, this language model became completely idiotic, just completely collapsed, making nonsense statements. So you could not do this. Okay, you could not use artificially generated data to do it. At least we haven't found. That's why GPT-5 have not been rolled out. That's according to Ilya. He said we run into this problem. So way in the future, how do we do this? Remember AlphaGo? From AlphaGo to AlphaGo Zero, AlphaGo was trained using real games played by professional players. AlphaGo Zero found a way to get rid of, to remove the need for human data. And it started to generate its own data using certain mechanism, So now the game is to find a way to generate data that are different from the ones generated by ChatGPT. So you can actually feed into the system to augment your training set. That's exactly what OpenAI is working on and many others. Once they were able to do this, I think AI will be taken to a completely different level, just like AlphaGo Zero has taken AlphaGo to a completely different height, okay? And when this is going to happen, I don't know, okay? I think, I actually think it's possible. Right now, nobody has been able to do it. But once this is done, we are going to see AGI, named Artificial General Intelligence. Humans will be completely irrelevant. Is this a future you want to see? I don't know. Okay, I don't. But computer scientists are working on this. Big companies are working on this. Okay. Thank you.
Thank you, Professor Wang. We are running out of time, so we will take the last one question.
Hello, Professor Wang.
Yeah.
Here.
Oh, yeah.
Thank you
Okay.
for
Yeah.
a very intriguing presentation. I really appreciate how you explain the mathematics in simple terms, the mathematics behind AI processes. So my question relates to the school mathematics topics that are needed to understand AI processes and mechanisms. As in the talk you gave, we understand that there's data-rich modeling, there's functions, and probability that's involved. So can you say a few words about whether calculus is applied in
calculus is applied. You see this, remember I had a, for the target you have this regularization term, right? It's usually based on derivatives. Just based on, the way you keep a function to be, not like this is to add a constraint on the derivative. Because if you do this, you have the derivative, cumulative derivative change is going to be very big, okay? So you actually put a term to dampen this, to force it into something that is not too oscillating. And that is calculus. Then the training itself is based on probability and statistics. Okay, so we use something called the gradient descent. We all know if you want to reach the valley, you find the steepest descent point and you just follow that path. That does not guarantee you're going to reach to the bottom because you can get stuck. The worst is you have flat thing like this, you have no gradient. Okay, you don't know where to go. Okay, so we use most of the time to find the low. To go to the lowest point, we use gradient descent. However, in AI training, because of the overfitting problem, we never use traditional gradient descent. We use something called a stochastic gradient descent. We randomly pick a bunch of samples and optimize along that batch of samples. Then we change the sample. We randomly select another group, then change the train using that. This way you get something that doesn't have overfitting. And plus the regularization term in calculus. That constitutes pretty much all the mathematics you will need. And the GAN is about fitting the probability distribution. And that's, again, math. Yeah. And neural network is linear algebra. Okay. Yeah.
Thank you, Professor Wang. Please take your seat. Today's lecture is coming to an end. On behalf of the Education Bureau, I would like to extend our sincere gratitude once again to Professor Wang Yang. I also encourage everyone to continue supporting and participating in the upcoming lectures in the Distinguished Lecture Series on applications of mathematics in STEAM world. We look forward to seeing you all again. One last reminder, if any teacher have not yet filled out the attendance form, please scan the QR code outside to complete it. Thank you and goodbye.